and it's about quantum computing emulation. Please.
So, just a few words to introduce myself. I am a theoretical physicist, retired, but with an embedded position that allows me to continue to do research. Part of my academic life was in but not quantum computing, quantum field theory as a theoretical physicist. Another important part was high performance computing. So when quantum computing became important, I concluded that the best way to enjoy my retirement was going back to research and combining my two competencies, okay? Now, unfortunately, I had prepared 5 or 10 minutes of code to show a number of things, but I will not be able to do that, I'm sorry. Okay, now talking about quantum emulation is hardly a new subject because research in quantum algorithms has been going on for 30 years already. And anybody doing any serious work in this subject has been emulating. Uli has the emulator that has been running for 11 years already. And in most, so I mean, and there are magnificent environments like OpenFermion, Qiskit, and so on that do very well the emulation. I have to explain to you why what is the emphasis I put in this subject. First of all, I wanted to have, when I decided to go to quantum algorithms, I wanted to have something very simple and efficient to play on my laptop. You don't see my laptop. To play on my laptop, to get involved. You know that in order to master the subject, you have to put your hands under the hood. But when I went a little bit more into the subject, I realized that this is a standard quantum system platform that we have today, the quantum platform operating as a coprocessor of a classical platform. And the point is that quantum algorithms are severely constrained on the quantum platform because of fault tolerance and decoherence. So I thought that there are very, very powerful quantum algorithms that cannot be run on the quantum side, but that can provide enormous added value to the simulation. And my point was to run them on the classical side. That means that this emulator has to have a number of requirements that makes it very efficient as just an ordinary quantum, as an ordinary classical platform to cooperate with whatever you're doing here and with the quantum computer. So this is the point, and this has determined many of my architectural choices for the software. So what I am going to do is a very brief overview of quantum computing emulation, mainly the content and measure choices of my libraries. I am not going to detail. Then I will also review very briefly one of the heavyweight algorithms that cannot be operated on the quantum computer, and that I will again and again and again use on the classical side to improve a simulation. And that is phase estimation. This is one of the most general and most beautiful algorithms we have in the game. And it is a very heavyweight in the sense that you just cannot implement it on a quantum computer. Then that will be very fast. Then I will present you the way the H2 molecule operating in my environment. I know that there are hundreds of papers on the H2 molecule. There is nothing new here, except that for me, it is a magnificent case because it is a computation that requires an enormous amount of floating point computation to compute a very small effect. And therefore, it was a critical test of the quality of my software. But in addition to that, is a fantastic place where I can talk about one of my improvements of which is what I call the gate fusion optimization. And the final point, what happened here? Have I done something wrong? The final point is just an example of a simulation, very, very simple, where I will show you how my algorithm can improve very nicely and can provide a significant added value to the simulation. Now, the first point is just a small point concerning the emulation. So let's assume that we have 3 qubits. That 3, instead of 3, you can think of 28 or 500, okay? And we imagine that we have a coherent state here. Each qubit is in a clear state, A1, B1, A2, B2, A3. I am doing something wrong here. I don't know. I touch.
Blank screen.
We measure. So if we apply a gate to the first qubit, for example, then we just touch this gate, and this system will automatically adjust to a coherent state. And namely, A1 and A2 will change to A'1 and A'2, B'1. If instead we are emulating the system, we are working with a state vector. This state vector does not exist here. Here, this is quantum matter that acts. It doesn't know quantum mechanics. Quantum mechanics exists in my mind, in my notebooks, and in the probably in the memory of my computer. But here you see that you have to change all the components of the state vector. So in fact, if you have n qubits, a single qubit operation here implies a 2 to the n operation on the state vector. So, there are 2 points here. The first one is that this maps to a big unitary matrix in Hilbert space. That's trivial, everybody knows that. And the second point is that you should not allocate the matrix, because if you do that, you are out of memory immediately. You have to construct the matrix every time that you need it. So the way to construct the matrix every time one needs is to look at the states, the binary representation of each one of the basis states, then identify the 2 states of the qubit that you are touching, and get all the pairs of addresses where the spectator qubits are the same. And you have to do that for all the possible configurations of the spectator qubits. So your initial operation, which was one application of the matrix 2 by 2, boils down now in this case to 2 to the n-1 operations on the state vector. So this is the simplest argument I have to show the exponential blow up of degrees of freedom in quantum mechanics. Now this generalizes to 2, 3, 4, 5 to other gates. So in general, the prescription is very simple. Just apply the gate to all the configurations in which the spectators are constant. Remember that there are a few constraints on quantum emulation, the qubit cannot be copied because there is no unitary gate that provokes this transition. We don't have any persistent memory, so you cannot store partial results. We have input issues because creating an initial state is easy if the initial state is given in terms of qubit states, but it's much more difficult if you have a vector, classical vector, and you have to make a quantum vector which has exactly the same component. This is the so-called data input, data load problem. There are severe output limitations because as soon as you look at the state vector disappears. If it is on the computer, on the quantum side. You just see one state. The state vector is a superposition of the states. You see one state, but the next time you look, you see the same state because the vector has disappeared. So we will come back to that later on. Let me now tell you about the emulator package that I have developed. It is just a C++ library running on laptops. It runs on my laptop here, and I can run up to 30 qubits on my laptop. And I was planning to show it to you, show how, but so that means that I have done the maximum in avoiding unnecessary memory allocations. Then I have four different libraries. One which is just shared memory with multi-threaded, which is fully operational. Another one which is MPI, distributed memory. You need to go MPI because as soon as you go to more than 30 qubits and so on, the state vector, every time you add a qubit, you double the size. So you have to go to MPI, and that is only operational. And this library also runs on my laptop. Then I put GPUs. So I have another library which I add the GPU, and then the final and the ultimate performance comes from MPI with CUDA, with GPU. I have made it sort that all the MPI and CUDA, I programmed in native CUDA, but all the MPI and CUDA complexities are hidden. End users don't see that, and there are very simple protocols to change, to move your application from one library to another. So you don't have to be an expert in MPI or CUDA. And then another thing that it is characteristic of my library is that I do not restrict the emulator to the standard set of 1 or 2 qubit gates. I go up to 5 qubit gates. That is highly non-trivial, but this is necessary in order to implement my gate fusion optimization. And no, so I will jump on the MPI issues because it is not important. And this is what happened in MPI. I have so let me now come to the phase estimation algorithm that I'm going to use. So the idea is that you have an eigenstate of a unitary operator, and you want to measure the phase here. What is going to happen is that we will use that to measure energies by using the evolution operator exponential of minus IHT for a given time interval, and from the phase we will get the energy levels. Now the idea of the algorithm is very simple. In any real number phi, because phi is between 0 and 1, every real number can be 0, 1 can be written as a series of power of 2, with binary values, V1, V2, V3, Vn, and the algorithm will determine that. Now, very quickly, what happens here is that if you have a set of simulation qubits, which is the physical system that you want to look at, you have to add a number of additional qubits which are there just to compute a Fourier transform. And then what is going to happen is that you are going to apply the unitary operator to the simulation qubits. If you do that blindly, you get nothing because you multiply the whole thing for an overall phase, which is irrelevant. This is applied controlled by the first qubit here. So that means that only when this qubit is in state 1, this is active. The same thing repeats with the other qubit. You apply U squared to the state only when the second qubit is on state 2, is on state 1, and so on. Now, in the next transparency, I have tried to show you what happens. I have here four worker qubits, and then you see what happens when you apply U to the places where the first qubit is 1, you have this. When you apply square to the place where the second qubit is 1, you have this pattern, and so on. And then at the end, you construct a state. You construct a state here, which is a very, this is obviously the Fourier transform of something, because it is taken with all the components of the powers of the phase. And that something, if you do an inverse Fourier transform, is a state with only one component, and this one component is at an index n, which has exactly the same binary expression as the phase. So we do that, we construct this state, we measure this state with probability 1, and from n, we read the binary expression of n, and we get the phase, okay? The guy who invited this, I don't know what he has in his mind, because it's completely twisted. Now, this algorithm is doesn't look very important, because after all, if you have an eigenstate, you have almost everything, so you don't learn very much. But the important point is that it also works when you don't have an eigenstate. And that is the real point of this algorithm. And the point is very simple. The point is that every single operation that I described is a linear operation. Applying gates, applying U is linear, and the Fourier transform at the end is linear. So if I have an arbitrary state, I can always expand it in terms of the unknown eigenvectors. I don't know what is A, and I don't know what is B, and I don't know what is psi1 and psi2. But because of linearity, when you think a little bit, you see that you are going to get now a result which is a linear combination. Instead of having one peak, you have two peaks at different places because they correspond to different eigenvalues, and the peaks are scaled by a squared and b squared. And a squared plus b squared is equal to 1. So in fact, this is giving you the way this vector projects on the unknown eigenvector. So the last final result is that when you apply the phase estimation to an arbitrary vector, then not an eigenstate of U, then the phase estimate algorithm returns the way your vector projects on the unknown eigenvectors given by the set of probability, and it also returns the exact associated eigenvalues, because from the binary expression of these indices, you can get the spectrum of the operator. So now this is very nice because this will we will use it in two ways. For example, imagine that you have an approximate, some computational method that has given you an approximate eigenvector. For example, the variational eigensolver, you have done a variational computation, and you get a result, which is not an eigenvector. You can check if that is a relevant eigenvector, because you should find a strong peak, and you should find a very small coming from the projection on the real eigenvector, and very small mixing with the other states. So that gives you a handle, a way of checking how could I say, how far or how near the approximate eigenvector you got is from a real eigenvector. But better still, it is possible, and that to emulate a measurement. That is to say, what you can do is you can by hand cut all the peaks you don't want, rescale this peak in order to have a normal one, and that is exactly the phase estimate transform of your exact eigenvector. So all you have to do now is to do the inverse phase transform, and you get the eigenvector. Okay, exactly. So that is what we are going to do. We are going to use this algorithm to monitor the precision of approximate computations done with the variational eigensolver, and then we will use it also, as in the way you will see, to project and to extract the exact eigenvectors. The linears, you heard about this famous linear solver algorithm. It uses exactly the same idea. Phase transform, manipulation, inverse phase transform to compute. This is a very difficult paper to read for a modern theoretical physicist, but the idea is really simple, and it is exactly the kind of idea that I have developed. Okay, now let me talk a little bit about the H2 molecule. I'm going to be very fast here because time. So what we are going to, I will just remind you very quickly the steps of quantum chemistry. The first point is to have a set of orbitals, namely the basis one particle states. In our case, what we are going to do is to take the hydrogen atoms, to put them at -r and +r, and to neglect all the excited states, and that's all. Now we just take the system, and we have the two states, spin up and spin down. So we have altogether 4 states, and we will describe a system with the occupation numbers 0 and 1, 0 or 1. That will mean yes, there is an electron here, no, there is no electron here. This is the starting point, and moreover, I will use the standard thing in quantum chemistry, the wave function of the ground state, which is a simple wave function, it's an exponential, will be approximated by Gaussians, because that is the only way we know to compute the coefficients in the Hamiltonian. Now, well, this is the traditional quantum chemistry Hamiltonian. We have for the electrons in the we have the kinetic energies, we have the interaction with all the nuclei, and we have the Coulomb repulsion. Let me. And the atomic orbitals we introduced before are not the good ones, because we know that the electrons are not localized. Wave functions overlap, and electrons can jump from one side to the other. So the first thing you do in quantum chemistry is an artifact computation that will give you what is called the molecular orbitals, namely the basis states which are linear combinations of the atomic orbitals, but which are distributed over the molecule. And in our case, the system has so many symmetries that we can guess them. It turns out that this state, which are psi plus or minus psi left and so on, this with this overlap integral of the two are the correct ones. These are just exactly the hardest. In this particular case, you can write them directly. Then, once you have taken those orbitals, the Hamiltonian is practically all diagonal because, definitely, this is a term of the kinetic energy plus interaction. These are the occupation numbers. So these three pieces are diagonal operators. These we have, these are the kinetic energy plus interaction with nuclei of each electron. This is the Coulomb repulsion between two electrons that are here in the plus state. B is the Coulomb repulsion of two electrons that are here in the B state, in the minus state. And this term, which produces a transition because it takes particles from here and put them here and so on. This is a traditional Coulomb exchange term, which has no classical analog. And the point is that D is a very small coefficient with respect to A and B. So we have an almost diagonal Hamiltonian with a very small and complicated non-diagonal part. And then this problem reduces to the diagonalization of this 2 by 2 matrix, okay? 2H because there are two particles here, 2H3 because there are two particles here. A is the Coulomb repulsion here, B is the Coulomb repulsion here, and D is the transition. So our problem of the hydrogen molecule reduces to the diagonalization of the 2 by 2 matrix. But on the emulator, we will need 450,000 gates to emulate this step. So I will solve the problem, trivial problem of the organization of 2 by 2 matrices, and then we will compute on the emulator and we will see what happens. So if you look at the 2 by 2 matrices, what you diagonalize, you have this. That is to say, on the excited state, there is no minimum. On the ground state, there is a minimum of 0.9 angstrom. That means that we are predicting that the size of the hydrogen molecule is 1.8 angstrom, and the physical, the experimental result is 1.4. So we are not too far. The binding energy also is within 20% of the exact binding energy. And then I will compare the result with what comes out from the emulation of the problem. Now, okay. I will pass on this. When you install the problem on the quantum computer and you do the famous J-box mapping of operators in such a way that you end up with a standard spin Hamiltonian in which you have the qubits, the two-state qubits, and the Pauli matrix is operating on that, and that's all. Then you have almost the same thing, except that there is a change of sign here. So the point is that emulating the diagonal terms is easy. Emulating this term is much more complicated because you need to emulate this term 120 gates. In fact, you have a circuit which has 15 gates, and you need to operate 8 times the circuit. You emulate once this famous term, and you have altogether you have altogether 120 gates. And if you count how many gates are when you have 8 auxiliary, 8 worker qubits, then you have the 120 times. This is the doubling of the time on the different qubits and so on. And this n here is what you need for totalization. And you have to take the time interval and slice it in petit steps in order to be able to approximate the exponential of non-commuting operators. And this is a standard thing in also. So this is the important point for me is that this formula, which looks very simple, that means that is saying you that the exponential of non-commuting operators is the product of exponentials if you slice the time interval in this way. So this naively looks like a 1/n precision, but in fact, it is 1/n squared. There is a nice paper that proves that this formula is accurate to 1/n squared. I use n of the order of 16, so 1/n squared is 4 parts in 1,000. So in my computation, I am producing systematic errors, which are 4 parts in 1,000. And then we do the computation. If you apply the phase estimate algorithm to the psi plus, to one of the 2 states that you have, the psi plus, for example, you get this. This is telling me that this state has a very strong projection on the true ground state, a 96% projection on the true ground state, and a 4% projection on the excited state. So this is, I am verifying that the mixing in my 2x2 matrix is very small.
This is at the equilibrium distance?
Sorry?
This is at the equilibrium distance of H2?
Yes, yes, but that happens at any distance, because at any distance I have the 2 states, and at any distance I can do that. That's the way I measure the energies as a function of the distance. When I do that, it's exactly, this is a list of exact values from the diagonalization of the 2x2 matrix, and these are the result of the emulation with 150,000 gates. And you see in general that except for this term and this one, all the other terms are below the 4 parts in 1,000 systematic error. Great precision, okay? So, fine, that means that I didn't make any mistake in programming my emulator for this problem. Now, we can do a little better than that. And we can replace the 120 gate, the 15 gate circuit by a unique 4 qubit gate, unique. And provided that I am able to compute this unique 4 qubit gate. If I do that, we reduce the computation in a dramatic way, because instead of swapping 15 times the Hilbert space with a small matrix to apply my ordinary circuit, I will be swapping only once all the Hilbert space with a 16 by 16 matrix, which is this thing. So what I do and what I develop is a way of replacing a circuit by an equivalent multi-qubit gate. And that introduces a fantastic performance boost, okay? And this is the reason why for deriving the software, I included up to 5 qubit gates in the game. And then fusion in 2 gates is trivial if they are acting on the same qubit. You just multiply the 2 by 2 matrices. Fusion in 2 gates, if they are acting on different qubits, is also trivial. You just take the tensor product of the 2 matrices. And instead of a 2 by 2 or 2 by 2 matrix, you have a 4 by 4 matrix, and that's it. That's trivial. What is highly non-trivial is fusioning partially overlapping gates. And I found the right tricks to do that. And this is critical because in all the qubits, you have the C0 gates which induce entanglement and which are at the origin of all the partial overlapping of many gates. So when I apply, these are the final execution times. I was planning to show you, I can't show that with my laptop, but unfortunately doesn't work with Zoom. With 4 computational qubits for the molecule plus 8 worker qubits, with just CPU transit for the 9 seconds. If I add gate fusion, I have a speed up of 5. In fact, on my laptop, it's 6, not 5. If I add GPU from here, I have a 10x speed up, because for 49 seconds, if I add a GPU to the CPU, I am down to 5 seconds. And if I do CPU plus gate fusion plus everything, it's just 1 second. So I decrease 50 times, roughly, the execution time of this application, okay? And this is because again, the fundamental reason is having something that can be operated in a simulation in hybrid system. So this is this 50 times speed up is not universal, it depends on the problem, but it is very efficient, and the combination of gate fusion with GPUs bring the whole thing down in a dramatic way. Okay, now I come to my final point, just 5 minutes left, which I'm jumping on that, which is a Hoover model. We imagine that instead of 2 hydrogen atoms, we have a chain of hydrogen atoms. And we are going to try to describe conduction band. So what we do is, first of all, we just don't care about the wave function. So we imagine that the wave functions are just delta functions. Either the particle is sitting here or it is not sitting here. If it is sitting there, we pay epsilon if the binding energy of the molecule. If it is not sitting there, it's 0. But in order to take into account the fact that wave functions overlap and that electrons can tunnel from one atom to the other, we add a term which subtracts an electron from a site and puts it in the next one. Okay? This is known as the type. This is the basis of the Hoover model. This is the trivial. And of course, we have a periodic boundary condition. That means that we have a jump from here to here in such a way that we have a circular ring topology. If you do that, then the eigenstate of this Hamiltonian are immediately obtained in 3 lines. And these eigenstates are the block waves, are propagating waves with momentum k, Ka. You see that this wave function here is a superposition of electrons being in all sides. So this is fully non-localized, and it is a propagating wave. These are the energies. And we have, if we have n sites, we have n possible values of the momentum. And this set of energy levels is called the Fermi sea. And the ordering is we have a ground state at k equals 0. Then we have 1, n minus 1, degenerate, 2, n minus 2, degenerate, and so on. And the problem that I want to look at is when we have 2 chains like that, one for a spin up, another for a spin down. And in fact, what I'm going to put in the quantum computer or emulate is a system where I have a number of worker qubits that I can use for some kind of accessory computation, like Fourier transform. Then I have n, a tight binding chain of n qubits, followed by another tight binding chain. This is a spin up and this is a spin down. And n and k plus n is the same side. And in order to take into account the Coulomb interaction, we just add a term that says if two electrons are face to face, then that goes to an energy U. A very simple parameterization of the Coulomb interaction. Now, the physical problem is very simply described because, in fact, when you don't have any Coulomb repulsion, the ground state, absolute ground state, is a symmetric ground state with the half a field. You have as many particles as you have as many electrons as sides, so half on the one side, half on the other. And if you don't have this, namely, if you, for example, have an unequal doping, then obviously what you are doing is passing electrons from this state to this one, increasing the energy. You are moving electrons to higher energy state. So this is the absolute limit. But if you add the Coulomb interaction, the thing changes, because if you do that, you pay a higher kinetic energy of block waves, but you have less electrons face to face. You have reduced the number of electrons that can be face to face, and you have reduced the Coulomb repulsion. So at some point, when the Coulomb repulsion is very big, this will gain against the other, and the system will collapse to a state in which all the electrons have the same spin. And that is an itinerant ferromagnet. Itinerant because the electrons moving, a ferromagnet because you have a given magnetic dipole moment coming from the electron. So what we want is to construct the ground state of the itinerant ferromagnetic phase, namely start from the free Hubbard model and increase the Coulomb repulsion until we produce the transition to an itinerant ferromagnet. Now, in order to, I'm sorry, I'm going to jump on this because this is a beautiful thing, but it will slow me down. So the first thing to do is to construct, to fill the Fermi sea, to construct the ground state of the to construct the ground state of the free fluoride. This is the first point. Yes.
5 more minutes.
Yes. Yes. 5 minutes. Yeah. So that is a tricky problem for many reasons, but these people here found a beautiful algorithm that does the job. I cannot describe the algorithm because the algorithm was singular value decomposition, given rotations, and so on. It is a very clever algorithm. I had it in operation. I was going to show you how it operates, but so believe me, we can immediately reconstruct the wave function of the Now, the second observation is that coming back, we have heard a lot today about the variational eigensolver, and you appreciated how complex and how sophisticated the research in this area is. But I want just to remind you that if I take an arbitrary state vector in any system and we compute the expectation value of the Hamiltonian, then you can write it in this way by eliminating C0 from this equation. And this is telling you that this expectation value is always an upper bound because it's semi-positive to the ground state energy. And it is equal to the ground energy only if this is 0, but this is 0, you have the exact ground state. So in all cases, the mean value of the Hamiltonian on an arbitrary state is an upper bound to the ground state energy. So what people do with the variational method is to parameterize wave functions and to minimize them with respect to parameters in order to obtain the best variational energy, the best upper bound. What we are going to do now is to use the variational eigenvalue to compute the ground state at u equal different from 0, and using the variational wave function given in this paper. The variational functions given in this paper are functions which take as a basic state the ground state, the ground state wave function of the free model, and then apply things, operators which are gates, which you already have in the emulator, which can immediately be used. So when I apply the variational minimization with respect to this variational wave function up to u equals 1, then I have an approximate eigenvector. Then I can do the test that I was talking about. I apply phase estimation to this eigenvector, and I see that this approximate eigenvector has a 91% projection over the true ground state, and a small projection over excited state. So I conclude, and then I have a second quality test, which is to see if the exact ground state energy, which is given from this number here, is below the mean value of the Hamiltonian given by the variational method, because it has to be below, because we know that the mean value of the Hamiltonian is always an upper bound to the exact energy, and we know the exact energy. So with this criteria, we can decide if this is a correct minimum or not. And then we keep it. Once we have this, I finish. Once we have this, we extract the exact ground state that you perform by doing this two-step procedure, phase estimation, emulation of the measurement, extracting, and then inversing the phase estimation to get the exact ground state. And then what we can do is, once you are there, we can use now the exact ground state that we have at T=1 as a reference state again, and do exactly the same thing to compute the ground state at T=2, and so on. This is the best way I found of handling this type of problem, because if we try to use the variational against order method for large volumes of U, you don't know. When you're looking for a minimal, the emulator, the optimizer can get stuck in a local minimum, and you have to do 20,000 checks to know what you are doing. In this way, we are controlling what we are doing, and we are sure that we are getting the exact ground state for large volumes of U. And to conclude, the last one, why do I want to do that? Why do I want to do that? Why do I want to have the exact ground state in the ferromagnetic? Because we want to go beyond structural calculation that use some dynamics. So what we want to do is to take the system which is in the ground state now and to send a system which is in the ground state and send an electromagnetic wave. The electromagnetic wave will interact with the dipole moments of the electron and will excite spin waves. And that can be done with linear response theory, like the computation of Green function and so on. And it turns out, I will not go through that, but you can solve this problem only with the phase estimate algorithm, only. It is sufficient to apply phase estimation to V times the ground state, size 0. So that's, unfortunately, I can't continue, but anyway, thank you very much for your attention.
Do we have questions?
Yes.
Thank you for your talk. I have a question about your simulation of QPE and QPE applied to the hydrogen molecule.
I'm sorry, I have problems of.
So, simulation of the hydrogen molecule with QPE. So, did you do the simulation with the polarization n equals 16? You know the trotterization, you mentioned you took n equals 16, right? Have you tried with n equals 1 or 2?
No, impossible. It's slicing, the number of slices of my science. It has to be 20, 30, 16.
It has to be?
Yeah, because of protein. I mean, if I think one,
Sure, you have a solution, but do you think it's possible on a real computer? Okay. Yeah. Okay. I have another question. So is it systematic for the ground state, also for the excited state? Will always be the same. whatever the geometry.
Simply by the fact that you are making an approximation in computing the exponential of an operator.
Mhm.
And that touches both the ground state or whatever.
All the spectrum. Okay.
I checked that. I computed also the ground, the exact state, and I checked